whereas at the output what you say, the health layer, actually the output of health layer is actually HL of X. Actually, it's not a hidden layer, but it's a health layer, because the health hidden layer is the output layer, and that is something but the activation of AL. AL is, in this case, it is A3, activation of A3, and that is nothing but your output f of X, which is depicted as Y cap. Okay. So this is actually, and generally what we do is we drop this X and we simply point it out as AI and HI. Okay, we don't, we generally drop this X. Okay, that X is understood. Now, next we move on to this data. Okay, so data, actually what you give the data is consists of two parts: the input X of I and Y of I is the output label, output label. So in this case, we are having n number of data, and Y of I, the Y cap of I is the estimate, what the output of the neuron. Okay, output of the network. So as I told you, output is depicted with a cap, whereas Y is the label. Okay. So the difference between the label and the Y cap, that will give you the error. Okay. So Y cap is the actual output by the neuron, and Y of I cap is equal to f of X of I. Okay, which is the output, which is the output of this weight W3 into H2. Okay. So actually, so it is a nested output. Okay, so you see that W3 into G. So actually, when you take this, say if you take this neuron, so this is connected at all neurons in this level 2. Okay, which in turn is connected to all other neurons in level 1. So it is actually a nested practice. Okay, so at this point you will have W1 X1 plus B1. Okay, that is given to the activation function at second layer, and that is again given as activation function in the third layer. Okay, so it is a nested function. Okay, so like that, and we will refer to the parameters. What are the parameters here? So till yesterday we are using theta as the threshold, but from today we will say theta as the parameter. Okay, the parameters that are learned in the neural network. So it is slight abuse of notation, but need not get confused. Hereafter we refer theta to the what you call the parameters. Okay. So in this case, what are the parameters? In this case, the parameters are W1, W2, W3. These are the parameters. The weights that are connecting the different layers is the parameter. So the weight matrix are the parameter at different layers, and the bias, the weights of the bias. Okay, weights of the bias are also the parameter. So our parameters are going to be this W3G, W2, W3, W2, W1, and B1, B2, B3. These are going to be the parameters. So W1 to WL, B1 to BL. So these are going to be the parameters, and it is represented as a set called theta. Okay. And algorithm, what is that we are going to use? So yesterday itself I introduced you to the gradient descent algorithm, and today we will take the backpropagation algorithm. Okay. And now we talk something about what is the loss function or what is the error function. Okay. So here you see that as I already told you, Y cap is the output that is generated by the neural network. We call it as the actual output. So Y cap, and you are also given the label Y of I. Y of I is the desired output for that input X of I. For that input X of I, what is the desired output or the label? That is Y of I. So the difference between the desired output and the actual output is the error. Okay. So here you see Y cap of Ij minus Y of Ij. So take the label of the ith sample. Okay, ith sample, you take the label and you find the difference. Okay, and that difference has to be squared. Okay, so squared error, because as you know, some errors are positive, some errors may be negative. So when you just add them without squaring, the positives and negatives, they get cancelled, and the actual sum of errors will be less. So the reason for squaring the errors is to make it positive. Okay, So the errors are always positive. Okay. So sometimes y cap will be less than y. In that case, the value will be negative. Sometimes y cap will be greater than y. In that case, the value will be positive. But when you square it, whether it's a negative or positive, everything becomes positive. And that you have to sum. That you have to sum. Okay. And you have to divide by the total number of samples, 1 by n. Okay. So when you do that, so what happens is it is a mean squared error. So that's a term we use, mean squared error. And it is denoted by this notation, script L of theta. Okay. Script L actually tells you is the some function of error function of the parameters. In this case, it is the mean squared error. Okay. And it is expressed in terms of the parameters theta, and the theta is here. Okay. So what is the loss given certain values of weights and given certain values of bias weights? Okay. So that is what actually the loss function is, and we have to minimize the loss function. We have to minimize. It's an optimization problem. It's an optimization problem. So wherein you have to minimize it, so that by way of minimizing those squared errors, you are actually tuning the parameters W1 to WL and B1 to BL. Okay, so that which achieves this minimum loss function, and that is when you say that my neural network has learned, okay, the whatever applications you are putting in. Okay, right. So these are some of the things that you have to keep in mind. Okay, so now you can recall yesterday the gradient descent operators, what we have seen yesterday, that when you talk about what you call a perceptron with a step function. So a step function is not a smooth function, I told you, so you cannot apply gradient descent approach, because when you want to apply gradient descent approach, we are interested in finding the gradient. You know what is a gradient? Gradient is the first order derivative. So so your function has to be what you call differentiable. If you cannot differentiate a function, then that function cannot be used in machine learning. Okay. So now, so this you can see. Okay. Say W of t at iteration t plus 1 is equal to W of t minus some eta of delta W. So delta W is the differentiation. Okay. So how much difference, how much error? Say I want to differentiate the weight with respect to the error. So what error I've shown in the previous slide. So I have to differentiate the error with respect to weight such a way that I get the maximum reduction in the what is differentiation? Differentiation is change of a variable, rate of change of a variable with the input. Here the input variable is W. W is the weight. Now how much, by changing how much of the weights I am affecting the output. That's what actually we are trying to do, and that change in weight is delta WT, and that delta WT has to be either added or subtracted to your the present WT to get the next weight, that is WT plus 1. Similarly, bias weight. The bias weight has also to be differentiated, and that has also to be adjusted. So B of t minus eta times delta of B of t gives you the B of t plus 1. Okay. So where this they have shown this, what is delta of t and what is delta of B. So delta of t is delta of W is actually the partial differentiation with respect to W, okay, of the loss function. And what is delta B? Delta B is the partial differentiation of the loss function with respect to bias weight B. Okay. So this is actually what is called the gradient descent approach, and this I have to do for some set of iterations or till some condition is satisfied. And here I told you this figure. Say you see how this if you start from this point, so in which the error is higher. Now as you move along, as you differentiate, the path that it actually takes is actually like this. It takes like this path and finally comes to a place where the error is minimum. Okay, so that's what they just compare the previous slide. That's what actually we are doing. Okay, say we are trying to minimize the error. Sorry, loss function. Okay, right. So here red represents higher error and blue represents low error. Okay, so this is actually the things you have to remember. And with this, we move on to the gradient descent algorithm. Okay, so yesterday I told you that this gradient descent algorithm, we are modifying W of t and B of t, W of t plus 1, B of t plus 1. So these two things can be put together because W and B, they are the parameters. So instead of calling W and B, what I call now is I call it theta of t plus 1, theta at time t. So where theta includes both, it includes the initial value of W and initial value of B. Okay, and finally we come up with a we differentiate and we come up with this value. Okay, now our theta is actually a matrix of this form, a matrix which is concatenated, say first level weights, second level weights, third level weights, and then finally first level bias, second level bias, and third level bias. So it is we are just juxtaposing the matrices together, and we call this bigger matrix as the parameter. Okay, and that is theta. Okay, so like this, now you can see that this we are initializing initially. So you can just refer to the previous one. This is initializing. So detail I have given. So we are just juxtaposing all the matrices W1, W2 up to WL and V1, V2 up to VL. Okay, and then we are doing this. Okay, where where the rate of change, where the change in parameter is equal to this. Okay, and now you may wonder how this matrix looks like. Okay, how this matrix theta looks like. So you just see the next figure. So here this is how delta theta looks like. Okay, so here the first one refers to the layer, number of the layer. Okay, so first layer, first neuron in layer 1 and the second neuron in layer 2. Okay, so delta W of 111 means the connection between, say it is this, if you take this is the first layer, so this is W11, this is W first, because first layer 111. Okay, and this is the first input and this is the first activation output. So 1, 1 refers to this, and the first one refers to the layer. So okay, so in short we call it W111. Okay, and what about this? This will be W112. Okay, this will be W113 or something like that. Okay, so it goes on like that. So here you see that up to this point, it is one set of matrix. Okay, and then you take the second layer. Okay, so it is W2, second layer weight. Okay, and in second layer, same, first input in the layer, second layer, and the first input in the third layer. So this also goes, this first index does not change for this value. It is only this 1, 1 change to 1, n, and 2, 1 to 2, n, something like this. So this is for the second matrix. So likewise it goes up to L. Okay, up to the Lth layer it goes, and this is the Lth, that's the top matrix. I told you the output, L is the output, and output, the number of neurons is not n, it is k. Okay, right. And this up to this point it is the W matrix, and after that you have say up to from this to this is the W matrix, and after that you have the bias. Okay, so bias, first layer bias to the since bias has only one element, so you don't need 3 indices. So first layer bias connected from the first layer to the second layer. So second layer will be connected from 1 to L. Okay, so like that. So this is actually bias is actually, it is a column matrix. Okay, so a column matrix. So if you look at this figure, you see. Yeah, if you take bias, so bias has only a single items. Okay, say this is one item, so it is an array, simply an array. But whereas W is a matrix. Okay. So this is bias. Okay, second, so that goes on like that. Okay, so when you put all these weights and biases together, so it looks like a bigger matrix. Okay, and that is what is called the delta theta. Okay, so it is composed of all this, and right. Okay, So every item is a partial derivative with respect to a particular weight. Okay. So with respect to a particular weight, it is a partial derivative of the overall loss function. L of theta is the overall loss function. Okay. So this you have to remember. Okay. So now how to choose the loss function? Okay. And now what type of loss function should we choose? Okay. That again depends upon the kind of applications we are doing. Okay. For example, you are say you are a critic and you are trying to rate the movies. Okay. So when I'm trying to rate the movies, so say I'm going to, there are several criteria. Okay. Say for example, the several criteria will be like this. Say is who's the actor? Okay. Say is some icon figure is acting. Okay. For example, Rajnikant or some iconic figure. Okay. Say Salman or something. So if that is a particular actor is acting, then that is a very important feature of that movie. Similarly, the director plays an important role. Okay. So some directors they are well received by the audiences. Okay, because of their previous success and all. So it may not matter who the mainstream actor is or who the mainstream actress. If the director is a famous one, then actually that influences the critic a lot. Okay. So based on several features, who's the actor, who's the director, who is the what is the script of that movie, or what is the genre of that movie? Okay. Like Bahubali is an old genre. Say similarly genre. Say for example a horror movie or something like that. So there are so many features in the movies. So that actually contribute to the rating. Okay. So rating could be 7.5 or something like that. Different ratings I can give. Okay. Now, say when you look at the output, okay, here the output is a real number. Okay. It is not true or false. Okay. So generally when I go for classification problem, the classification problem is true or false. That means I'm trying to classify whether it is a pen. Sorry, whether it's a cat or a dog. Okay. So in that case, the classification is whether it is a cat, yes or no. So the output is a binary output. Okay. But here, and that we call it as a classification problem, a binary classification problem. In the classification also, we can have categorical. For example, I can talk about fruits. For example, the next figure I will show you. Yeah. So here you see, I give a input the fruit, and here I say whether it's an apple, mango, orange, or banana. I want to categorize what kind of fruit it is. Now here, this is categorical, and here you see, if the first element of this array is 1, then it means apple. If the second is 1, that is a one hot vector. We call it by the name one hot vector. And if the first element is 1, then it is apple. If the second element is 1, all other elements are 0. It's mango. If the third element is 1, it is orange. If the fourth element is 1, it is banana. But the only thing is that only one of the element can be 1, whereas all other elements have to be 0. Okay. So this is a kind of categorical output, and we call this as a softmax output. Okay, it's called a softmax. So the function is softmax. Okay. But whereas if you talk about the previous whether it is a cat or not, it is a binary. Okay. So there are only you need only one output cell. If the output is 1, it is yes. If the output is 0, it is not. But whereas if when the number of elements branch, say when you have more than 2, in that case you have to go for a softmax function like this. Okay. And but for this problem, you see that this is movie rating, and here the rating of the movie we always give it as a 7.5 or 8.2, so it's a real number. So this is not, it is here. It is this is something like a prediction problem, okay, or regression. So generally in machine learning we have two types of problems. We have seen regression and prediction. Okay. So when you talk about prediction, it is actually a regression problem where the output is going to be a real value. So examples could be temperature of a day, predicting the temperature of a day, predicting the humidity of a day, predicting the rainfall in a particular day, or predicting the stock price for a particular item. So all these things, the output is going to be a real number, okay, and so it is a regression problem, and in this case it's a regression problem. So our arrays, the outputs are not limited to 0 or 1, okay, like unlike a classification where the output will be 0 or 1. In case of softmax also, the output will be 0 or 1 for a particular element, okay. So in case of a regression problem like this, then what kind of loss function can you apply? So here is this loss function we generally employ. What is that we generally apply? The mean squared error. So as I showed you last slide, this is a mean squared error that will be the choice as the loss function for this particular problem, in which the output is a number, output is a real value. Okay. Generally, regression problems are what you call the prediction problems. Okay. But when it comes to binary classification, or when it comes to softmax, at that point you cannot use this mean squared error as a loss function. There we have to use some other function. Okay. So what will be the loss function? So here in this case, you just take this, where the output is a categorical classification of more than 2 items. So here what will be the suitable loss function? Okay. So here the suitable loss function will be what we call cross entropy. Here the suitable loss function is called the cross entropy. Why is the cross entropy? The cross entropy, we call it cross entropy because this is actually a probability distribution. Okay, this is the probability distribution. So the probability distribution is 1 for Apple, 0 for all others. Okay, so that's the probability. So probability is what you call condensed. Probability is condensed for Apple, and it becomes 1, whereas all other things is 0. It could be like this also. It could be 0.99 here, and it could be 0.0001, 0.001, and 0.001. Like that also I can have. Okay, but here this is sharp. Sharp means crisp. Why? Because all other elements are 0, and this probability of Apple is 1. So I say that this is actually a probability distribution on 4 variables. Okay. Similarly, but what will be the output of the neural network? Output of the neural network will not be this. Exactly. So this will be 0.98, this will be 0.01, and this will be 0.01, and this some number. But when you add all this, it should be 1. That's what actually the probability distribution is. So this will be 0.97. Suppose 0.97. This is 0.1. 0.01, this is 0.01, and this is 0.01. When you add all these things, you get 1. So in that case, you see this is 0.97, but whereas we require 1. So here we cannot apply what you call the mean square error. So here what you apply is cross entropy. Finding cross entropy. What is finding cross entropy is you're comparing 2 different probability distributions. How different 2 probability distributions are. Okay. If the 2 probability distributions are not differing much, then we say that these 2 are same. Okay. So, for example, if this value is 0.97, this is 0.01, not 1, not 1. In that case, this is the same as this. Only thing is that it changes minorly. It's just a minor change in the. But when it is the cross entropy of both the distributions, they will be similar. Okay. So we use cross entropy for this functions, for categorical functions. But whereas if it is a regression problem like this, then we use the what I said, mean squared error. Okay. So these are the 2 things. Okay. Now just you can see this. So yeah. So what is the? Therefore, we should ensure that. So now in case of this problem, so here y is your. This is y label, but what you get y cap is another probability distribution which is changing slightly. Okay, in that case, how similar these 2 are, that you have to compute. Okay, that is called cross entropy. And here you see that the output activation is, in this case, is linear. In case of real values, linear, and In case of probability, it is softmax. And the last function used is mean squared error and cross entropy for softmax. So here, this is softmax. Inside this you have a softmax algorithm, and we use for comparing the output, we use cross entropy. But whereas in this case the outputs are real, in that case the activations are linear. But the comparison is what? The comparison is mean squared error. Okay, so this you have to remember. Okay, so this is so mean squared error and the cross entropy. Okay, I think you will not have any doubts till now. Okay, so we go on to the next topic, and here we get into the before we get into this thing, we have to see get into the back propagation algorithm. We have to see the intuition behind back propagation algorithm. So first we see the intuition or the motivation why back propagation. So back propagation is a very good algorithm. Actually, longer. I told you in the history type, it has been invented in different forms and it has been applied again and again and several people have worked on that. They have refined this algorithm. So it has been discovered and rediscovered over a long period of time. Okay, and that's the most famous algorithm as far as neural networks are concerned. Okay, even today when we are talking about CNN or RNN, still we use back propagation. So now when I talk about back propagation, I told you there is an error between the y cap. Y cap is the actual output and y is the desired output. So there is a difference between y cap and y always. That means when the network makes a error, the difference between y cap and y will be more. Okay. So in that case, who's responsible for this erroneous output y cap? Okay. So for example, we have taken the example of a cross entropy. So this is a cross entropy setup where minus log y cap is actually our y cap of L is our loss function. Okay, we are not using mean squared, we are using the cross entropy. Now, if an error comes here, okay, then who is responsible? The output layers are responsible. Of course, the output layers are responsible. But so you ask the output layer, why is that you are doing this, giving this erroneous answer? Is the output layer alone responsible for that? But yes, but it is partially true, because output layer does not see the input directly. So yeah, output layer does not see the input directly. It sees the input after the input has traveled through a set of hidden layers. It sees only what the hidden layer below it is presenting. It sees only this thing. Okay, so what is that actually? So the output layer does not see the input as it is. It sees only what is being presented to it by the layer just below the output layer. So it will say I know as far as what I have done correctly, but what this layer, the layer below the output layer has given me. Okay, and what is that layer below this output layer has given? It has given H2. H2 is the output of the hidden layer, and that is being presented to the output layer. So it will say they say, you see this output. So y cap is nothing but the output activation of, see, H of L minus 1. Here in this case, L is 3. So 3 minus 1 is 2. Okay, H of 2. Yes, H of 2 is this one. H of 2 is this. So W of 3 is this into H of 2 plus the B of 3, the bias. So these are the inputs to the output layer. So if the output layer makes a mistake, then it is the responsibility that these values have to be changed. Okay, the weights and the bias weights have to be changed. Okay. So you may ask the same question again. You ask the same question to this layer. Okay, you ask the same question to this layer, and this layer will say, no, what I have got, I have not seen the input directly, but I have seen what this layer has given me. Okay, so now it will say, my output H2 depends only on the output H1 and W2 and B2. Okay. So that's what I've shown in the second figure. Okay. So the output of this depends upon this. And when you ask this layer, it will say that I have made the decision based on what is given as input and this weights W1 and B1. Okay, so these are the weights. Okay, so what is that we are doing? Actually, the error is getting propagated. So our thing is, if you want to change the error, you want to change the error of the output, you have to adjust the weights and biases here. You have to adjust the biases here and adjust the biases here until you reach the input. This you cannot change because input is fixed. Okay. So you have to reach until the input. And you know, there's a trick in algebra that says there's a trick in your calculus. So it says the chain rule. Okay. So the chain rule is say I want to find the rate of change of error L of theta with respect to y cap. Okay. Okay. So with respect to y cap is the output. Find the loss function, change in loss function with respect to output that can be changed with the rate of change of output with respect to A3 because the output depends upon A3. Okay, output depends upon A3. Okay, and what is this A3? A3 depends upon H2. A3 depends upon H2 and H2 in turn depends upon A2. Okay, are you following? A3 depends upon H2 and H2 depends upon A2. A2 depends upon H1 and H1 depends upon A1. Okay, so A2 depends upon H1 and H1 depends upon A1. So you can put a chain rule. Okay, you can use the chain differentiation rule. And what is finally A1 depends upon? A1 depends upon the rate of change of A1 depends upon W1. Okay, A1 depends upon W. So here you see now there are three. This is what you get when I take the output layer. This is the second hidden layer. This is the first hidden layer, and this is the input layer. Okay. So now you see that now when you can cut off all these things will get cancelled. This del y cap, del A3, del H2, del H2, all these things will get cut down, and finally what you will be left with is dl theta by dw111. So that will be left with. So now effectively when you change this weight, by changing this weight, how can you change the error? So this is what is the back propagation. This is the intuition. Okay. So this happens for every layer. Okay, so when I do for this layer this, when I do for this layer, it will be this. So now I can tell you that it is something like this. So we need to find the gradients with respect to the output units, find the gradients with respect to the hidden units, find the gradient with respect to weights and biases. Right? So this is what we have to do. And so I'm doing it in a simplified manner. So I've just taken the example for a 3 by 3 when you have the total number of elements as 3, that is the number of neurons is 3, then you see that this is what actually our finally a gradient with respect to weights and biases will look like. Okay, finally it will look like this. So here this delta W, delta with respect to the weights at the kth layer, with respect to the weights at the kth layer will be like this, where k is the layer number, so it will be like this. Okay, and similarly bias. So this is the bias. Okay, so here you see that with respect to bias B of k. Okay, so delta with respect to bias B of k will be this array. So this is what we are computing. Okay, this is what we are actually computing using the chain rule. Okay, and now we get into the actual algorithm. And here you see this actual algorithm is actually the gradient descent algorithm. So okay, so you initialize the theta. Okay, maximum iterations or initialize the theta. which is just stacking or juxtaposing of your weight vectors and your biases, and then you repeat this loop until maximum number of iterations. Or you can use some criteria. When the error is so small, you can give a criteria for the error. When the error reaches this much, then stop. So this stopping criteria could be anything. You can choose whatever stopping criteria you. But here the stopping criteria we have taken as 1000 iterations. And then you have to find the forward propagation. Now, what is a forward propagation? You have to find, say for example, here I tell you, forward propagation is you have to find, apply the input, compute A1, compute H1, compute A2, compute H2, compute A3, compute Y cap. That is forward progression. So you have to find the forward propagation. So of this theta, so you have to find H1, H2 up to H of L minus 1, A1, A2 up to A, L and Y cap. So these are computed. All these things are computed in the forward propagation. And then in the backward propagation, okay. But you know that when you do this forward propagation, you know that this Y cap is not equal, or it's not close to Y. Or where Y is, what is Y? Y is the label, desired output. It is not, a Y cap is not close to Y. So therefore, what is happening is there's an error. Now this error has to be rectified. So for rectifying that error, I have to find the differentiation. I have to find the differentiate the error with respect to the parameters theta. Theta is W and B. So that is done by the backward propagation, which uses these values, which uses H1, H2, HL minus 1, A1, A2, AL, and Y and Y cap. Okay, so we are computing all this in the forward propagation, and the backward propagation, we are actually using these values to find the gradient of weights, okay, using which you can change the weights. You can change the weights at every level. And then finally, you use this delta theta t to change the weights. So this is actually the back propagation algorithm, okay. So it has two passes, one forward pass and one backward pass, okay. And this we do for a set of, you can do this for the entire training set, okay, in which I called it is a batch size of 1. I can do it for the entire training set for all, say suppose I have 1000 images, then I will do this for all 1000 images, finally compute the change and then apply the change. Or I can make mini batches. Mini batches, 1000 I can divide by 10. So I have 1000 divided by 10 is 100. So I can have groups of 100 samples. For every 100 samples, I can compute delta theta t and I can update the value of theta t. Or I can take, for simple, I can take one sample and make the change to theta t. So depending upon what you make, it is called batch normalized, it's called batch mini batch training, or stochastic gradient descent training. So when I take only one sample and change my weight, it is called stochastic, SGD, stochastic gradient descent. When I apply gradient descent to the entire set of samples, suppose I have 10,000 samples, I have used 10,000 samples and make the changes. It is called vanilla. It's called vanilla gradient descent. Okay, so vanilla gradient descent or mini batch gradient descent, or you can call it stochastic gradient descent. Okay, depends upon how much samples you take to adjust the values of the parameter. Okay, so that is actually these terms you may be hearing. Okay, now what actually happens in the forward pass? What actually happens in the forward propagation, we are going to see here. So you see here that we are computing the A of k and H of k. Okay, so A of k and H of k. So where Y cap is the activation at the final level. Okay, so you have to find A of k and H of k using the equations what I've shown you before. A of k is equal to B of k, the bias at level k, plus weight at level k, into activation of the previous hidden layer, H of k minus 1. And where H of k is just the what do you call, the function of the A of k. Okay, so whatever activation function you are using, you can use that function and find that h of k. So this is simply a forward pass is a simple loop. So for all hidden layers, say I'm going to do for k equal to 1 to L minus 1. Up to L minus 1, it is hidden layer. Lth layer is the output layer. Okay, at the output layer, I'm computing y cap at the lth layer. So this is forward propagation. Now, once you get all h of k, a of k, and y cap, now you can use the this algorithm, backward propagation. So I got h1, h2 up to h of L minus 1, a1, a2 up to al, and y cap. And I also get what is y, because I compute the error. So now you compute what is the loss with respect to activation at the output layer, which is given by this formula. So this derivations and all I have skipped because it takes a long time. So any standard book on back propagation, you will know that this del of L theta at the output layer is given by this expression. Okay. Similarly, k is equal to from the hidden layer L, that is from L is the output layer to the first layer. You do this. This is from back propagation. In back propagation, you find L of Wk, okay, a delta of Wk, that is loss function with respect to Wk, okay, using the formulas. And again, these formulas are actually what I have shown you already here. What I've shown you here, okay. So these are the formulas that actually, and use them, and you find the delta of a loss function with respect to Wk. Wk can be WL, WL minus 1, WL minus 2 up to W1. Okay, and similarly bias, delta B of k to B of 1. And finally, once you have found all these things, now what you have to do is you have to so this is computing gradients with respect to parameters, that is weights. And then you have to for computing this, you need compute parameters with respect to the below layer. Okay. So you have to use this because here you are using h of k minus 1. So you have to compute that h of k minus 1 and compute gradients with respect to the layer below. So, and here you see that to compute h of k minus 1, I require a of k. So I have to find this. So like this, I find this from layer L to 1. Okay, that is in the forward pass, you are finding the activations, output of the hidden layers, activation of the hidden layer, and the output. You are using those and the error, and you are differentiating it, and you are adjusting the weights and the activation function, because you need all of them because it is a chain rule. Okay, so to find this, I have to find this. To find this, I have to find this. Like this. To differentiate A2, I need A1. To differentiate, differentiate A2, I need H1. To differentiate H1, I need A1. Like that. It goes on like that in a chain rule. Okay. So I have to use that chain rule in the back propagation and find the gradients. Okay. And finally, I reach, when I complete this process, entire process for one set of training set, like for example 1,000 images or say 10,000 images, if I do this for one, it's called an epoch. When epoch is actually the number of samples that you have. Okay, say for example, if you take a mini batch, then the number of epoch, say your gradient will be found only for a batch size of say 100. Okay, so in that case, when you complete all 1,000, then we call it an epoch. Okay, so generally we do in several epochs. Okay, say you can take 10 epochs or say sometimes 5 epochs. Okay, where each epoch can be a complete vanilla set, or it could be a mini batch set, or it could be a stochastic gradient. Okay, so this is actually the concepts behind training. Okay. Next, I enter into the regularization thing. So here I wish to take some, I think 1 hour is gone. So actually I wish to take around say 10-15 minutes to 10 to 15 minutes to complete this regularization, because it's a small topic. Okay. So first of all, before I get into regularization, I want to talk about what is regularization. Okay. Say I told you that when we are talking about the loss function, So I told you there are several loss function. One is the mean squared error, another is one is the cross entropy. Okay, so these are the loss function. Now our job is to minimize the loss function with respect to our parameters. Minimize the loss function with respect to parameters. Now, so I am going to minimize my loss function. So this is my loss function, and L tilde is actually the regularized loss function. Okay, whereas L is without regularization. So now, so when I am, say for example, if you have a complex model like a model like of CNN or a big neural network with multiple layers, generally what happens is the model gets fit to the training set very well. It actually mimics the training set. Okay, so what I say mimics the training set means it learns the training set very well. Okay, and when you give a sample which is not from the training set, in the test set or the validation set, you give a sample which has not been shown to the model at the time of training, this model will perform badly. Generally, that's the case. Okay, generally that's the case when models perform badly. Okay, so in that case, we say that it is the model is doing very well on the training set, but the model is not doing well on the test set. Okay, or I will say it is another way of saying that the model is more specific to the training set and less general to the problem. Okay, because what training set you choose is actually only a subset of the input that is available in a problem. For example, say you are classifying lung cancer nodules. In that, lung cancer nodules actually it is a problem, and that problem can have millions of images, X-ray images. But what you have access to is only say 1,000 or 5,000 images. So the 1,000 or 5,000 images in the training is not sufficient to model the entire, it's not the correct sample of the entire lung nodule X-rays. Okay, so if your model gets more suited or gets more fit to the training set, it will perform badly if you give a new X-ray image, because that X-ray image it has not seen. Okay, and therefore it may perform very badly. So that is the reason we say it is the so here you have to remember the two things. When a model performs perfectly well on training set and very poorly on the training test set, we call it a variance. We call it variance. Variance is high. We say the variance is high when the model performs badly on training test set and very good on the training set. Suppose the model performs very badly on the training set itself, then we call it is highly biased. Highly biased. So the problem of highly biased is that you may have chosen the wrong model. Okay, the problem may be a complex problem, but I may choose the wrong model. By choosing the wrong model, my model will be biased. So when a model is biased, its training error itself will be large. Okay, but if the model has high variance, we mean that the model is doing very well on the training set, but is doing very bad on the test set. So the error between the training, when you talk about the accuracy at training, the accuracy at training will be 99. But when you take the accuracy at a test, it will be only 85. So there's a difference of 15% in accuracy, and therefore we say that this variance is high. So that is what is called bias variance trade-off. So a model should not be biased, a model should not be variance. So this is what actually the thing is. Okay, and generally when the model is complex, it tends to become highly variant. If the model is simple, it becomes biased. So generally you have to choose the right model, and once you have chosen the right model, then you find the L of W. Okay, now what is the objective? Our objective is to minimize L of W, is it not? Where W is the parameter, we have to minimize L of W. Okay, but what is that? When you're training, you're trying to minimize it. Okay, that means when L of W on training is almost reaching 0, the loss is reaching 0, that means your model is very fitting itself to the training that. In that case, so what I will add is I will add some penalty. So this is the penalty. So when I add a penalty, so what happens? What is this penalty? I'm trying to minimize something, But to that I am adding a some component, okay, and because of adding that component I am trying to maximizing it. So actually my objective is minimization of the loss function, but I am adding a penalty so that it does not minimize very exactly, does not minimize very exactly. So that is actually this penalty term. Why it has been chosen like this is will be quite clear in the next step, because you are going to take the gradient differentiation of the loss function with respect to w. So when you differentiate with respect to w square will become 2w. The 2 and 2 gets cancelled, so it becomes alpha w. So that's what the alpha w. That's why we put this half. Okay, it's because it's a squared, and generally we call this as L2 squared. Okay, level 2. Sorry, not level 2. L2 norm. It's called the L2 norm, and that is squared norm. Okay, Frobenius norm. Actually, we call it a Frobenius norm. So we use this Frobenius norm so that our differentiation, our gradient of this tilde L will be having this parameter. And what is alpha? Alpha is a constant you choose. That depends upon the problem. Okay, I'll tell you in the next slide what is this alpha. So you add this penalty term, and when you're updating the weight, you see initially this was not there. Initially this element was not there, so only you had this element in the updation of weight, but now you add this penalty term also. Okay, right? So this is actually the difference. This is what is called L2 regularization. The objective of regularization is to make the model not very perfect. Okay, so it may look very counterintuitive, saying that why should not we make the model very perfect, because a very perfect model will not do very well on a general problem. That's the problem. So we never allow the model to get perfectly fit into a training set. Okay, because our training set is not reliable. And this is what actually you have to go through certain mathematical rigor, so to prove what is this geometric interpretation I will just give here. So it is actually this W tilde. W tilde is actually matrix after normalization. Okay, W star is the W tilde is the weight matrix after regularization, and W star is the weight matrix before regularization. So before regularization, you see this is your optimal W star. This is your optimal W star. But this W star is a matrix which can be decomposed by some methods, matrix decomposition, scalar value decomposition, or you can use Q decomposition, something like that. And when you decompose, you get the eigen values. So these are the eigen values. So this D is the eigen value. Okay. So without regularization, the alpha will not be there. Alpha will not be there. So you'll have 1 by lambda, 1 by lambda 1, 1 by lambda 2, 1 by lambda. Okay. So the alpha will not be there in if you don't regularize. So in that case, you know that this matrix will be in what order? It will be increasing order. Okay. Then if you know singular value decomposition, this is a diagonal matrix. This will be the highest. Lambda 1 is the highest eigenvalue. Lambda 2 is the next highest eigenvalue, and lambda n is the least eigenvalue. So since lambda 1 is the biggest eigenvalue, 1 by lambda will be the smallest value, whereas this will be a big value. This will be in the reverse order, and you have, because we are taking an inverse of that. That's the reason. Okay. Now, by regularization, what is happening is this is what is happening. Okay. Right. Now here you see that if lambda is much greater than alpha. Alpha is the constant you are choosing. Penalty term is a constant in the penalty term that you are choosing. If you choose alpha such a way that if lambda is much bigger than alpha, where is lambda? Lambda is eigenvalue. So eigenvalue means some features are prominent and some features are not prominent. These features which are prominent will have higher lambda value. Features which are not prominent will have smaller lambda value. If lambda is much bigger than alpha, then in that case, this term will be almost equal to 1, because alpha is much smaller than lambda. So therefore, this will be almost equal to 1. If lambda is much smaller than alpha, in that case, this term will be 0. So what is that? What is the rationale behind is some features are getting enhanced, some features are not getting regularized. Those features which have higher lambda values are not getting regularized, but those features which are having lower lambda value means those features which have less eigenvalue, means which are less prominent, those features are getting penalized. So you are penalizing the features. You are not penalizing all the features in the same manner. If the feature is prominent, you are penalizing it. If the feature is not prominent, you are penalizing it. So that's what actually you are doing. Okay. Thus, only significant directions, larger eigenvalues will be retained and others will be left out. When you want to put it in a diagrammatic manner like this, so what is happening is your optimal weight W star without regularization gets rotated. You see, it gets rotated and shrunk. It gets rotated and shrunk to W tilde. W tilde is the optimal weight after regularization. Okay, so now you see that there is a difference between this and this, because and you see that my I have succeeded in making my my weights not very optimal, not exactly optimal, but somewhat suboptimal. Okay, when I make my weights suboptimal, or when I make my parameters suboptimal, I'm achieving generalization. So that is the main idea behind regularization. Okay. And other types of regularization, just I'll go fast. Suppose if you don't have much samples, using data augmentation methods, I can create samples. For example, by rotating by 20 degree or rotating by 65 degree, shifting it down, shifting it to left, blurring the image, okay, and say adding some colors and all. So what I can do is I can do some what you call manipulation on the given label, and I can create varieties of it. So now what I have more data. Typically, when you have more data, it's better learning. Okay, so it's well for images and object classification. It also works very well for speech. Okay, so but what the problem is, for image, speech, you can create them, you can add noise, you can do something, but for some data it may not be so clear. You may not know how to generate new data from existing data. Our parameter sharing and tying is another way of improving our regularization. So what is that? So here you just take this image, and instead of having weights for each and every pixel, what I do, I scan the image using this filter. This is a small filter is shown here. Using the small filter, I scan the image. So the same filter is actually shared by the parameters are available only in the filter. So the same parameters are shared by all the pixels of the image. Okay, so this is what is called parameter sharing, and this happens in our CNN. We'll come to that. When I come to that, we'll discuss. Okay, so convolutional neural networks, they do this. Okay, then when you come to autoencoders, at that time I'll tell you that autoencoders is a way of storing complex data in a simpler form. Say an image with say 1000 pixels can be represented with just 10 pixels or 11 pixels, say 10 or 20 pixels in a compressed format. Okay, then from this I can again see this is my original image, this is compressed image, and from the compressed image I can even extract the original image, but I will not get the entire image, I will get XCAP. Okay, so there will be some difference between X and XCAP. So this is called autoencoders. In autoencoders, what is the problem is the weights of this matrix and the weights of this matrix are same. You cannot have a matrix with different weights here, and you cannot have a matrix with different weights here. So these matrix weights that are at this junction are same as the weights at this. This is called parameter tying. Okay. Generally, parameter sharing and parameter tying is a way of improving regularization. Then adding noise to input. So you may ask why I want to add noise, because I want to correct my input. Same as data augmentation. So data augmentation, what we have done? We have added some noise, we have rotated the image, or we have scaled the image, or we have shifted the image, translated the image, blurred the image. So it's as if you are adding some noise to the image, okay, and working with that. So these are some mathematical rigor that is needed to prove that by adding noise, we get almost the same thing. You see, by adding noise, I get an expression that is expectation of y cap minus y. Expectation is mean of y cap minus square, mean square, plus you see some term. Okay, and what is this term? This term is similar to the term that we have used in regularization. This term. Okay. So by corrupting an image, you achieve the same thing by what you are achieving a regularization. So adding noise to the input is actually a best way of regularization. You can also add noise to the output, because the output is what you are taking and comparing with the input. Okay, output is what the actual output y cap. That y cap is you are comparing with y. Suppose now you corrupt the output. Okay, say for example, this is a hard target. I want to achieve 0, 0, 1. For example, in a cross entropy loss function, I want to achieve this 0, 0, 1. But don't do this. Don't do this achievement. This is called hard target. Don't do this. You corrupt the output. Say don't. You take some epsilon, small error. You add to the 0. So it's epsilon by, or you can divide by some value. Okay. So something you can do this, and this is a soft target. That means I'm not interested in achieving the exact input or exact output. I'm not interested in achieving the exact output, but I'm interested in getting an output which is similar to my exact output. Okay, so not optimal. So this is again another way of improving regularization or making your neural network more general. Okay, so that's called you always try to achieve soft target. Okay. So what you're trying to do is you're subtracting a small value from 1 here. Whatever value you have subtracted, that value is divided by 9, because there are 10 elements. So one element you are subtracting some small value and dividing by the rest of the elements, are 9 elements, and you are putting it there. Okay, so it's just an algorithm to make a soft target. Okay. Another method, those who have learned machine learning will know that generally you can do something called ensemble or bagging. So what we do is we use different logistic regression. We create different models. There are 3 models. For example, if you are using logistic regression or or a decision tree or whatever it is. So you can create different different models. These are different models. You divide the training set. You divide the training set, what you call as sampling with replacement. So you divide the training set for this. The training set is not same for all the models. So for one set is given here, one set is given here, one set is given here. You take the output of the first set, output of the second set, then take an average of that. Okay. Then you get the final. So this is what is called ensemble. Ensemble means using multiple units, multiple models, with the different subsets of the training data, and finally you're just using some centrality measure, and you're just taking an average. Okay, so that is the ensemble method. I will just tell you, an ensemble method is almost similar to our dropout in neural network. You might have come across dropout. So with the neural network, if you want to do, instead of doing with the same model like this ensemble model, I will take different models. So this is a different neural model, this is a different neural model, this is a different neural model. All 3 models I will train with the different set of training sets. Then I will take an ensemble. Okay, that is one thing, but this is little tedious to do. So what we do is we take a complex model, and for during training, by random, I just shut off some of the neurons. For example, this neuron is shut off. When I shut off this neuron, all the connections to that neuron die. Okay, so I'm left with only a subset of the weights. So my weights are not complete. It's not completely connected. Now, since some neurons have been shut down, so the weights are now, number of parameters have reduced. Okay, this is for one set of training, say for one epoch. Okay, in the next epoch, some other neurons will be shut off. So when you, depending upon which neuron you are shutting down, you will get different networks. And the output will be, you will get a different outputs, and then you can take an ensemble. Okay, so in dropout is actually a way of implementing ensemble modeling which we are used in machine learning. So how much you want to drop out? You can drop out nodes with some probability. Say, for example, sorry, here I'm retaining some nodes with 50% probability. Means what? 50% of the nodes I'm dropping out. Or sometimes you may use some technique by which you can say for some hidden nodes, I say 80% I retain, means 20% I drop out. Okay. So like this, I can use dropouts for my different epoch, and I can get different values, which is better than ensemble, because in ensemble you have to create different models, but here you don't create models, you create only a one model and you apply dropouts. Okay, so dropout is a way of regularization which is same as ensemble modeling. So I think I just covered. So if you have any queries, then I'll answer the queries. So what is left is two important architectures that we'll see tomorrow, that is neural networks the day after tomorrow. So that will complete the course. One thing actually, people have asked for references actually. So references I've just collected and give it to you tomorrow or day after tomorrow. Okay, because so there are two books actually. One is Deep Learning by Nielsen is one book. Another book is Deep Learning by Ian Goodfellow. Ian Goodfellow, all of you may be knowing it. So these are the two best books for deep neural networks. So I'll give you the details maybe tomorrow. And apart from that, there are very rich resources which are available on YouTube. You can for that also I'll try to give you. Okay, some videos which are created by MIT. Actually, the people, they have done a lot of research in deep neural networks. They have put a lot of videos are available in thing. And from our NPTEL also, the IIT Madras Professor Mitesh Karpra, actually his materials are also very good. Okay, so tomorrow I will just put a slide about the various references that are available, and I'll put you tomorrow. Yeah, I don't see much of queries that are available in the chat box. Okay, so I think we can take leave. Thank you again so much for joining this session. Okay, so see you tomorrow.